Ever wonder why you don't sink straight through the Earth or even the chair you're sitting on right now? The same quantum effect that prevents you from falling through solid matter helps stars fight gravity. And stars are literally everywhere. Literally! Current estimates suggest there are around 10 to the 23rd stars in the observable universe. That's 100,000 billion stars and counting. Welcome to part 1 of our 3-part series on star formation, black holes, and galaxies. In today's episode, we'll explore star formation, the birth, life, and eventual fate of these celestial beasts. Let's dive in. After the Big Bang, which we covered in our last video, the universe was mostly hydrogen with some helium and trace amounts of lithium. Over time, these hydrogen atoms clustered into giant nebulae, massive clouds of cosmic gas. Gravity pulled these atoms together, and collisions between them released heat, thereby creating an internal pressure or resistance that counteracted further gravitational collapse. This concept of resistance is central to a star's entire life. Throughout its life cycle, 4 different types of resistance counteract gravity at different stages. In early stars, thermal pressure from particle collisions, then fusion, which is released by nuclear reactions, electron degeneracy pressure, which is the same quantum effect that stops you from falling through the floor, and finally neutron degeneracy pressure, which occurs in extreme densities in dying giant stars. At this early protostar phase, the main form of resistance is thermal pressure, fueled purely by the collisions of hot gas. For a star similar to our Sun, this phase lasts around 10,000 years. During this time, the protostar grows increasingly dense and hot, preparing to ignite fusion in its core. Eventually, our budding star reaches temperatures of around 15 million degrees Kelvin. Kelvin is just degrees Celsius plus 273, so 15 million is really hot. Fusion is when atoms combine to form larger atoms. So imagine that we have single protons or hydrogen atoms slamming into each other at tremendous speeds. These 2 protons fuse, with one converting into a neutron, producing deuterium, 1 proton and 1 neutron. Deuterium then collides with another proton, forming helium-3, which consists of 2 protons and 1 neutron. Further collisions occur until helium-4 is created, which is 2 protons and 2 neutrons, and forms a helium core surrounded by a hydrogen shell. Now that nuclear fission is underway, the star enters its main sequence, where fusion pressure acts as the main form of resistive force against gravity. Smaller, failed stars called brown dwarfs never quite reach the threshold for sustained fusion, remaining relatively dim and cool. For stars below about 8 solar masses at birth, life unfolds over billions and billions of years. 1 solar mass is simply the mass of our Sun, 2 times 10 to the 30th kilograms, or 333,000 Earths. Let's look at our Sun for an example. Our Sun first fuses hydrogen into helium in a stable balance during main sequence. Next, in the red giant phase, after running a little bit low on hydrogen, the star's core contracts while its outer layers expand. Helium fusion kicks in, creating heavier elements like carbon and oxygen. Eventually, the star's outer layers drift off, forming a luminous planetary nebula, a gorgeous cloud of ever-expanding gas. But don't get fooled by the name. No plants were used in the making of this nebula. The leftover iron core stabilizes as a white dwarf thanks to electron degeneracy pressure, the quantum principle that also prevents you from falling through the floor. Essentially, electrons can't be squeezed into the same quantum state, so they push back against gravity, capping the star's mass at around 1.4 solar masses, the Chandrasekhar limit. Electron degeneracy pressure can be visualized by imagining electrons trapped in an ever-shrinking cloud around an atomic nucleus. As gravitational pressure increases, the electron cloud compresses. According to the Heisenberg uncertainty principle, the more precisely we can find an electron's position, the less precisely we can know its speed or momentum. In other words, forcing electrons into a tighter volume makes them move faster. This ramp up in speed translates into an outward push, electron degeneracy pressure, that counteracts gravity and keeps small stars and, in everyday life, you, from collapsing. Without this, even stars less than 1.4 solar masses would implode under their own weight. Yet, for larger stars, stars born above 8 solar masses, gravity soon overpowers electron degeneracy pressure, leading to a far more dramatic and much shorter lifespan of a couple million years. With much stronger gravity, heavier stars form bigger elements sooner. To start, hydrogen turns into helium during main sequence, helium into carbon during the red supergiant phase, carbon into neon in mere centuries, neon into oxygen in about a year, oxygen into silicon in a matter of months, silicon into iron in only about 1 day. The star's core stops at iron because the nuclear force holds the neutrons and protons together more tightly when they form an iron nuclei than when they form any other kind of atomic nucleus. Essentially, everything above iron experiences fission and breaks into iron. We now enter the tipping point. In smaller massive stars, up to about 20 to 30 solar masses at birth and up to 3 solar masses at death, the iron core collapses under its own gravity. Protons and electrons merge in inverse beta decay, creating neutrons plus a flood of neutrinos. Gravity has compressed the star so fiercely that neutrons are all that remain in the actual core. Neutron degeneracy pressure, analogous to electron degeneracy pressure but at higher densities, takes over. Essentially, the neutron cloud condenses, making the neutrons speed up. During this process, the atom's size shrinks from 10 to the negative 8 centimeters to 10 to the negative 13 centimeters. This collapse pulls in the star's outer layers, which crashes on the dense core and rebounds into a colossal explosion. This supernova shines 10 billion times brighter than our sun and is one of the brightest objects in our universe. Supernovas are also responsible for creating many of the heavier elements that we've come to know and love, like silicon, which we use to build computers. After the bang, the remaining core is now a neutron star, barely 20 kilometers across, but yet up to 3 solar masses. Imagine compressing 1 million Earths to fit within the confines of New York City. If the star's final core is over 3 solar masses, not even neutron degeneracy pressure can hold it up. The star collapses into a black hole, effectively punching a hole through the fabric of space-time. We'll explore black holes more in an upcoming episode, so make sure to subscribe. Putting it all together, stars begin as hydrogen atoms at around 10 to the negative 8 centimeters in size and weighing 2 times 10 to the negative 27 kilograms. These little fellers form clouds that battle gravity using thermal pressure in protostars, then shift to fusion-powered main sequences. Smaller stars eventually rely on electron degeneracy pressure, becoming white dwarfs, while massive stars ends with neutron degeneracy pressure or collapse into a black hole. The remnants, supernova debris, or planetary nebulas seed the cosmos with heavier elements, forming new stars. The whole thing is basically a giant cosmic recycling program. These stellar remnants help shape entire galaxies over billions and billions of years. Stars, black holes, and swirling clouds of gas band together under gravity, forging the massive structures we can see across the night sky. When we look up at the stars, it's awe-inspiring to realize that each of those tiny pinpoints of light is a star in some stage of its cosmic life cycle. Our Milky Way galaxy alone has up to 400 billion stars, and there are an estimated 10 to the 23rd stars in the observable universe. Like our ancestors, can we derive meaningful insights from these celestial beacons? As Carl Sagan once said, "We are all made of star stuff. We are a way for the cosmos to know itself." Thanks for joining me on part 1 of this journey on star formation. And the next part of our 3-part mini-series, we'll be talking about black holes and galaxy formation. So make sure to hit that like button, hit that subscribe button, and that notification bell so you won't miss out on our next video. Until then, you know what? Have a good time. Yeah, you know what's all we're doing here? We're just living life, doing crazy things, and